This is the Lac Operon. This is the regulatory gene Lac-I. It produces the repressor in the active form. It happens to be near the operon, which is unusual. This is the promoter. It is here that RNA polymerase and CAP, catabolite activator protein, attaches. This is the operator. Here is where the active repressor attaches and stops RNA polymerase binding. These are the three genes. They code for enzymes involved in lactose utilization: beta-galactosidase, permease, and transacetylase. This is the repressor in its active form. When in this form, it binds to the operator. This prevents RNA polymerase from binding to the promoter and transcribing the genes. This is allolactose. It is the inducer of the repressor. It inactivates it. It is in the system when lactose is present. It's an isomer of lactose. Allolactose binds to the active repressor. This cannot bind to the operator because it is inactive, leaving the promoter free for RNA polymerase. RNA polymerase is free to transcribe the genes encoding enzymes for lactose utilization. This is an example of negative control because the repressor is made in the active form, and it remains like this until allolactose inactivates it, leaving the operator free for RNA polymerase to transcribe the genes. This structure is called CAP, or catabolite activator protein. It is inactive unless bonded to CAMP, or cyclic adenosine monophosphate. E. coli can use glucose or lactose as sources of energy. CAMP levels are high in E. coli when glucose is scarce. This means more lactose utilization enzymes must be synthesized. When in its active form, CAP joins to the promoter. This higher the affinity of RNA polymerase to bind to the promoter, and hence increases the rate at which the genes are transcribed. Because of CAP and CAMP, the rate of transcription is directly affected. This is an example of positive control.